Good. So can everyone hear me at the back okay? Cool. Fantastic. Wonderful. Well, look, thanks everyone for coming today to Conversations on Consciousness, how the CCN community can contribute. Good. So the purpose of this event is to try and bring together two communities. So first, the CCN community with expertise in computational modeling and AI, but who until relatively recently have engaged relatively little with the question of consciousness as a community. And second, the consciousness science community who work on consciousness, but who are only beginning to grapple with the implications of AI for consciousness research. Now, consciousness science is a flourishing discipline that has been flourishing since the mid-1990s, so there's a great deal to learn from it. But on the other hand, this isn't going to be an uncritical introduction, right? It's open to us to question the assumptions that consciousness science has made over the last 30 years and ask what consciousness science may have missed along the way. So the plan for today is we're going to start with an introduction by me, then 3 talks covering 3 Templeton World Charity Foundation adversarial collaborations by Lars, Steve, and Megan, and then we're going to have a general discussion at the end. Good. So to kick us off, the fundamental question, what do we mean by consciousness? Well, the classic definition in the literature is the idea that consciousness is something it is like for an organism. So Tom Nagel says, an organism has a conscious mental state if and only if there is something it is like to be that organism. But what does this mean in concrete terms? So much of the focus of the literature and the focus here today is going to be on vision. So that question becomes a slightly different question. What does it mean to have a visual experience? And I think it's useful to think about the following case. So when you see an object, right, you have a visual experience of the front of the object, right? You have an internal rendering of the object in your head, but you don't have a visual experience of the back of the object, right? The brain doesn't render that internally in the same way. And so really the debate comes down to understanding that internal rendering when and how it occurs. Good. So what do we want to explain about this internal rendering? And there's essentially sort of 2 questions you might think about. So the first are why questions. So why does the brain give rise to conscious visual experience? Whilst the second are how questions. How does the brain give rise to conscious visual experience? And these 2 are subtly different questions. So the why questions ask what's known as the hard problem of consciousness. So why does a physical thing, our brains, give rise to a subjective internal experience in the first place, right? The basic idea being, if we think of physics as just a bunch of atoms hitting against each other or electrical signals being passed around, why should that be associated with an internal experience? And the worry is that we can't give a computational answer to that question, potentially for 2 reasons. The first is some people just say the fact that the brain is a piece of meat fundamentally matters, right? And they say that consciousness is simply a property of biological systems and not artificial systems, even if the artificial systems implement the same computations. But the second argument says, look, even if we apply consciousness to artificial systems as well, a computational account, it just gives us laws, right? It doesn't explain anything. It just says, do X and you get consciousness. It doesn't explain why doing X should give rise to consciousness in the first place. But perhaps laws of consciousness are all that we can achieve and all we can hope to achieve at this stage, right? And that's good enough. So trying to understand the computations that underlie consciousness, and we're also going to sidestep the biological versus artificial point by just looking at the neural correlates of consciousness in the human brain. But before we do, we also have to be aware of another distinction, the distinction between phenomenal and access consciousness. So if a stimulus that people typically report as being conscious is associated with activity in the prefrontal cortex, is that indicative that consciousness is going on in the prefrontal cortex? So some people say it is, right? That neural activity is indicative of phenomenal consciousness, so subjective experience. But other people would say, no, that activity in the prefrontal cortex is just about your ability to report or think about your visual experience and not the visual experience itself, right? So that's access consciousness as opposed to phenomenal consciousness. Good. And really what we're looking for are the neural correlates of phenomenal consciousness. So let's apply these lessons to the visual pathway and indeed to the topics you're going to hear today. So first, the signal travels from the retina to LGN to V1, and then we have a quick feed-forward sweep. And both of these stages are in red because the literature typically treats these stages as unconscious. And I'm going to briefly discuss these. Then we're going to turn to 3 Templeton World Charity Foundation adversarial collaborations. So after the feed-forward sweep, we have local recurrence and re-entry. And this is in yellow because some people think it's associated with consciousness whilst other people don't. And Lars is going to discuss first-order theories of consciousness that associate consciousness with this stage. Finally, we have global processing, which is in green because everyone thinks it's conscious. And Steve's going to discuss higher-order theories of consciousness, which associate consciousness specifically with this stage. Good. But really, the big debate in the consciousness science literature is between first-order and higher-order theories, right? So how do we determine and adjudicate between them? Put simply, are the neural correlates of consciousness in the front or the back of the brain? And so finally, this is the question that Megan's going to address in her talk. Good. So before I hand over to Lars, Steve, and Megan, I just want to quickly explore this question, right? Is feed-forward processing really unconscious? Because what I want to do today is give you 3 reasons why I believe, at least, that the current consensus that it is unconscious may be incorrect. So first, I want to kick off by asking rather mischievously, is CCN doing zombie science? So what do we mean by this? So here's the feed-forward sweep of the ventral stream, right? It's been an incredible source of inspiration to the CCN community, to AI in general, right? It really underpinned the AI revolution, and many of us here are working on the feed-forward sweep. And yet, it may come as a surprise to you, and certainly came as a surprise to me, that the consciousness science community treats this as largely unconscious. So here's Victor Lame, here at Amsterdam, who says, the feed-forward sweep is the brain at its best. It shows how it can function as a reflex arc, not very different from the simple sensory motor transfer that occurs in the knee-jerk reflex. Similarly, Crick and Koch say, zombie modes, and they're treating this feed-forward sweep as a zombie mode. Zombie modes show that not all motor outputs from the cortex are carried out consciously. In a zombie mode, the main flow of information is probably feed-forward. And the question is, do we really want to accept this? So think about a Formula One driver, right? They can respond to the lights going out within 0.2 seconds, so only really quick enough for feed-forward vision. But do we necessarily want to claim that this is unconscious? Or indeed that all rapid responses to visual stimuli are unconscious? Indeed, Steve and Matthias Michel have recently embraced this conclusion, arguing that whatever consciousness is for, it's not for rapid responses. And so the first question for us is do we want to accept this conclusion? The second question is, do we have, if you're going to claim that the feed-forward processing sweep is unconscious, do we have a good test of unconscious vision? And typically the answer is yes, it's objective invisibility. So what does objective invisibility claim? Well, it claims that neural activity in the feed-forward sweep is often consistent with 2 things. First, subjective invisibility, so subjects being unaware, right? They can't report that they saw a stimulus. But secondly, and more importantly, the stimulus having no effect on their behavior, right? So the assumption is, if people aren't aware of it, it has no effect on their behavior, we can be relatively confident that it's unconscious. But I want to question whether this is the case. So think about the following case, right? You're looking at a white screen, and I make it just a fraction darker, right? But you don't notice it, it has no effect on your behavior, so it's objectively invisible. Is it unconscious? Well, I do it again, and again, and again. And at some point, you want to say that what you're looking at is the dark screen rather than the white screen you started off with. But the problem is that none of these individual steps right, is conscious according to the objective invisibility criterion. So none of these individual steps should have changed your visual experience away from the initial white screen. So that seems to be a key concern with objective invisibility as a criterion, and a reason why I don't think we have a very good test for unconscious vision. But the third point is, even if we don't have a good test for unconscious vision, perhaps we have a good test for conscious vision, right? We know what conscious vision looks like. It looks like visual constancies, okay? So constancy is like color constancy, size constancy, and depth constancy, which all supposedly show that our visual experience is very different from simply what's on our retinas. So take color constancy, right? The disk in the center in these two illusions side by side is the same on your retina. It's the same color on your retina, even though you see the one that's on the left is yellow and the one that's on the right as blue. And so you might think, if we're looking for the neural correlates of visual experience, we should be looking for representations in the brain that label this disk as yellow and this disk as blue, right? And this may implicate a bit of the feed-forward sweep, perhaps. But I think we need to go even further than that. Indeed, I would argue that we should be looking for areas that don't label the disks differently from one another. Why would I argue for this? Well, the fundamental question, you'll remember, is what is the visual system rendering, right? So if the visual system was really rendering these two disks differently, and rendering one as yellow, one as blue, literally, as it were, sort of yellow pixels, blue pixels, then as we alternate between the two versions of the illusion, we should experience a flickering, right? Back and forth, yellow, blue, yellow, blue, yellow, blue. By contrast, if color constancy isn't affecting our visual experience, merely a cognitive effect, then we should expect the appearance of the stimulus to remain constant as we alternate between them, even though we can determine when it's yellow and blue. And what's interesting is this seems to be closer to our experience. So I'll give you a quick go, right? If you look at the center, right, you're alternating. The stimulus isn't changing its appearance, right? It's not flickering, but at the same time you can clearly say, give you another go, it's going yellow, blue, yellow, blue, yellow, blue. But because there's no flickering, I'd argue that really we should be looking for areas where our visual experience treats these two things as the same. And the same lesson applies to visual constancies, right? So these cars are the same size on your retina. And so you might think, if you're looking for the neural correlates of visual experience, you should be looking for areas that label this car is large and this car is small. But again, I think that's a mistake. Because if the cars really were rendered large and small in your visual experience, it'd be very difficult to explain why, when we add rectangles to the cars, right, the rectangles seem to be at least less distorted, or perhaps not distorted at all, compared to the cars. Okay, so the idea being that if the cars were literally rendered larger and smaller, then anything surrounding them would have to be equally distorted. So again, I think we should be looking for areas that don't have these constancies rather than areas that do. Good. So to summarize, color constancy and size constancy potentially implicate early visual processing if you don't believe that they affect our visual experience directly. And there's another argument from depth constancy as well. But in order for that, you'll have to come down to my poster after this event, or check out the project website. Good. So if you're interested in these arguments, there's also a paper, V1 is the egocentric cognitive map. And with that, I want to hand over to Lars to tell you all about first-order theories of consciousness. Thank you.
Good morning. Thanks, Paul, for setting up the scene and for the invitation to this beautiful venue and nice conference. So I will be reporting about the Intrepid, World Templeton, World Charity Foundation, adversarial collaboration. Why do I hear this? Is there anything I can do? Okay, yeah. Is that better? Can you hear me in the back? Okay, thanks. We will be looking into investigating the spatial consciousness across the visual blind spot, and the interpret is comparing information integration theory with predictive processing. So the protocol paper you can find with this QR code, and the bigger interpret project comprises of 3 theory leads, 4 experimental leads, and I'm going to introduce, for the purpose of the talk today, my Glasgow lab. That's Lucy Petro, Clement Abatacola, and Belén Montebes de la Cruz. And this team have been working on our side to investigate the space perception around the blind spot. And we were supported by the replication lab around Patrick Kavanagh in Toronto, and that is with support of Smirmant Tripathi in Bradford and Mario Start in Toronto as well. The 3 theory leads are Giulio Tononi, Carl Friston, and Cyril Pannertz, comparing information integration theory IIT against 2 flavors of predictive processing. That is predictive processing active inference, Carl Friston, and predictive processing neurorepresentationalism with Cyril Pannertz. So AI, predictive processing active inference, is proposing that there are shifts in conscious perception require active inference, like shift of attention, shift of eye movements, to reduce uncertainty, which equates to belief updating. And there will be one experiment within this interpret that is focusing on that kind of hypothesis with emotion-induced blindness. When this illusion kicks in, the percept disappears. The question is, how does it reappear? How does the object that disappeared reappear? Is it faster if you do active inference, or if you do have a passive movement of the stimuli that just disappeared? I won't be talking about this today, but this is more specific on their predictions. And neurorepresentationalism is the idea that perception arises from the interplay between low-level and high-level sensory inferences, but it has a very important multisensory component. So perception, visual perception, is situated with any other senses as well. And we'll come back to the hypothesis for the experiments that I'm proposing later on. And central to some of the experiments I will show is IIT, who says that our experience of space is supported by the brain's areas whose units are like grid-like connectivity. And that's very essential to this. Now, we started in 2020 having discussions with the different theory leads, and it was quite inspiring for me as an experimental lead, I was just listening to the different theories, and we were searching for relevant challenges for this theoretical framework, and myself feeling maybe more home in the predictive processing camp. Was exciting to listen to the IIT camp to kind of understand the way they approach the question of consciousness. And I think it's a good way of doing science. Instead of having a confirmation bias and doing the same things, like this is a depiction of information in the internet, it is good to stretch a little bit out and to talk to to other conceptual challenges. And I think we came out with some good challenges that we then had to turn into experiments and do the experiments and replicate the experiments. So we proposed the hypothesis that were pre-registered early on, and we wrote the protocol paper, and we refined many of the details. The devil's always in the details, as we know as experimentalists, and you'll see some of that later on. And then we we had real big sample sizes and all pre-registered, so then we had a clear response, a clear result, until we thought of one more control, and so there's a bit of a twist, so stay with me, and we can think about whether proper science should stop here or here. So to start thinking about this, a central paper is from Andrew Horn and Giulio Tononi, 2019, where they asked the question, why does space feel the way it does? And with this question, they're approaching the hard problem of consciousness. The question is our experience of space supported by brain areas whose units are linked in a grid-like connectivity structure? So the cause-effect structure of this grid, does that support the perception as we feel it? Now, if you start from a phenomenological point of view, you perceive space, let's say, as a dark universe in which there are some light spots, and they have properties. They are there and not elsewhere. Spots together can be fused to an object. They can be distant. In between two objects, there's empty space. They can fuse and have joint boundaries. Regions, locations, and distances can fall out of those kind of properties. And the phenomenological space and the grid-like space can be assigned or compared, and in IIT, the idea is that they are identical. So any given conscious state is associated with a maximal reducible causal effect structure, is the hypothesis. Taken, for example, from a distance, you can see all the possible stages that the grid can represent between two dots for that kind of space distance, and that makes it feel distant from one another. But in changes from that follows that changes in connectivity, even in the absence of changes of activity, should lead to a warping of experienced space. And that is the central hypothesis that we are addressing. So in the typical approach of IIT, there are the 5 axioms in which you start from a phenomenological structure of your experience and look for a physical structure that can reflect that phenomenological structure. But then it goes further to ask the question, what happens if this structure is changed and altered? And in our experience, in our interpret, there are 3 experiments that are targeting this. The first one, which I will not talk about, is doing mice electrophysiology, and it will look in how mice perceive space, and it will inactivate inactive neurons, and by that test one of the central hypotheses whether space will be warped. The third one, 2B, looks at space perception around lesions in primary visual cortex. And the one I will be talking about, I proposed to Giulio, why don't we use a lesion that everyone has, and that is the blind spot, and use that in healthy volunteers, and see whether space is warped around the blind spot. And so this is the outline, 3 theories. One theme of experiments, but we are testing the space around the blind spot with 3 different examples: distance, area, and location or motion. And all of those experiments are replicated across 2 labs, independently and parallel. So to start the design, let's look into the blind spot, the physiology behind this. For everyone who's a vision expert, this is a little bit of a recap. And for everyone else, it's a bit to understand the backdrop. So the experiments will be like this. Subjects are in front of the screen. They have an eye tracker to make sure that they keep the fixation. It's essential. Now, if you present one spot on the right visual field, for example, that enters the left part of the left and right eyes, the retina, and is projected to LGN and then to the left hemisphere of V1. So in V1, primary visual cortex, we have, and I use from Horton's lab now, cytochrome oxidase staining of a subject that only had one eye, and after death you can then stain those ocular dominance columns for that healthy eye. And so this is the activated ocular dominance columns in a flattened V1 for the left eye. And you can see in the middle a structure that is a very, an island that is very much activated. Dark means activated. And the ocular dominance columns of the other eye I show now in green. And so that's how we usually see the world. In the V1, it would look at the right visual field, and you have the ocular dominance columns covering every space in the visual field. Now, if you take out the stimulation of one eye, in this case the left eye, then you see the whole. So you need to close one eye to be able to see the blind spot, and this space here would then be the blind spot, and we are now thinking about designing experiments at which we are stimulating over the blind spot. So the blind spot is, of course, where the ganglion cells leave the retina, and there are no receptors, and you can see that here. You can map it with fMRI. And here it's mapped out in semantics, in visual space. Now, for example, if we place 4 dots here, they are then processed in the right hemisphere. And so you don't see a blind spot, but if you close one eye, for example, and this is terminology that's important, if we close, if we watch the stimulus with the contralateral eye, so we close the ipsilateral, so now the right eye looks into this scenario, the blind spot is always on the ipsilateral to the seeing eye. So the blind spot in this case now would be on the right side, so outside of the stimulated area. It would be over here, so not at the stimulus, so we can use that as a control. And vice versa, if we close the right eye, now it's ipsilateral. Ipsilateral means that's the crucial condition in which the blind spot would be just in between 2 of those dots, and 2 of them are outside, and we are doing a distance comparison between the lower 2 and the upper 2, which one look further away. And if you want to perceive the blind spot yourself, I've been in this room yesterday to check this out. It should work in the sense you need to close your right eye, and you're in row 1, you're in row 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Last row should be 16. And if you fixate on the number, close your right eye with your right hand, then this clock on the wall should disappear. I tried this with the technician. He said, "Yeah, I can read the time, but that's not enough. It should totally be absorbed by the surrounding wall. It should disappear," which by itself I think is an indication of phenomenological indication of context-dependent predictive coding or filling in. But we're not looking at filling in. The question we are interested now is if you place 2 dots around that clock, or a little bit higher or a little bit lower, will they appear to be different in size? And how many could see it? Did it work? No, yeah, okay, great. So how we do it in the real experiment, we have red-green glasses, we have a fixation cross, and we have some additional stimuli that help to stabilize the percept. In this case, we show the blind spot after mapping as a stimulus, and so the 2 eyes see this in this scenario, but since the blind spot falls exactly onto that, perceptually, that's what the subjects are seeing. And whenever this, if they don't keep the fixation, this stimulus would come out of the blind spot and would be a very visible stimulus, and then they termine the trial. Before you do that, everyone has a little bit of a different sensitivity for red and green, so we adjust that by adjusting the luminance. As I said, we map out the blind spot, so we have a stimulus that we adjust to the blind spot in size and so on, and then we leave a small boundary to make sure that they can do the trials without aborting them if they have microsaccades. So that's the setup. Now the predictions. Theoretically, we are looking into psychometric curves, psychometric functions. The question would be, is the one bigger than the other? And ideally, you would have the curve crossing at the center. That indicates that both the comparison, the foil, and the target are perceived in the same size. So any shift from the center would be a size difference that we're looking for. And the other is a precision effect, let's say, that was brought in by predictive processing AI, saying, maybe I can't sample so much around the blind spot. And so your generative model is, it will come up with the same solution, but it's just sampling it a little bit more noisy. And so that would be a more uncertainty, would mean a flatter curve. So you get it about right, but it's slightly more uncertain, so it's flatter. So those are the two things we are looking for. Now, we have differences in connectivity around the blind spot. I showed that with the cytochrome oxidase staining. And the question is the hypothesis of IIT specific to only one eye or both eyes? And they said it's a difference in connectivity, so we propose it will be different in both conditions, whether you show it to the one or the other eye. So IIT predictions is the ipsilateral, so the most crucial one, is a decrease in size. Ipsilateral precision is decreased. The contralateral is also decreased, but the contralateral precision is not affected. And they gave also some confidence how important it is. It's a kind of, a pretty non-trivial prediction to say that this, space is distorted, I would say. But we'll test that in a moment. And so, as a reminder, ipsilateral means the blind spot, the light plot is in the middle, and here it's stimulated. Okay, so that's what IIT is predicting. And now the predictive processing camp, in principle, the idea is you generate internal models that are making good predictions about the world. And if you get it wrong, you get a prediction error fed back up in the hierarchy, and the internal models try to adjust to it. So by that account, if you get the size consistently wrong, your internal model should update to the prediction error, and over time you should learn, and it should reduce that. So both neurorepresentationalism and active inference are in general predicting that there is a reduction, that it shouldn't be affected. So the prediction table in detail looks, neurorepresentation was a bit timid, saying, okay, there could be a slight effect, slight or non-significant effect, so didn't really want to commit, but only on the ipsilateral and the contralateral, there should be no change. And Carl Friston said, okay, there shouldn't be any decrease. There should only be a change in the precision, because sampling, around the blind spot, you don't have as much population that feed into the internal models, and you get a little bit more uncertain. But there should not be a shift in the distance. Those are the predictions. Now let's go through the 3 experiments quickly. First one is looking at area, size of area. And in the top row, you compare the area to an area in the center. You adjust that. And it is either around the blind spot in this case. So you have this area size, and you adjust it in different steps to the center until it's perceived as identical. Or you do the same experiment outside of the blind spot at the reference area a little bit above, and do the same thing. So now, before I show the results, I would like you to bet on whether you're expecting to see a difference in the size or no difference. So all the ones that think there might be a difference in the size around the blind spot, please raise your hand. Okay, so that's okay. The ones that think there won't be a change. Okay, it's roughly equal. Okay, I'm glad that we do this before, because there will be the hindsight effect, right? So of course, everyone, there are some who can make up their mind, but in a minute, everyone would say, I knew it. So this is the result. So there's absolutely no effect, no size difference. So we replicated. There are a little bit difference, 32 subjects in Glasgow, 32 subjects in Toronto, overall no effect. But a very consistent effect of an illusion that we come back to, it's not going through the center. You need to make the foveal stimulus a lot bigger to match to the peripheral one. So it's about 1.2 times bigger. So the fovea needs to be bigger to match the peripheral. It's a known effect, so that's replicated. So how does it compare to the predictions? So the bias was predicted to be seen smaller from IIT. That didn't happen. And predictive processing, non-representationalism was a bit predicting both, so they can't score much here. This is for ipsilateral, and for contralateral, again, IIT said there should be something, there wasn't, and the others said there isn't anything, and they were right. Now, in the precision, so the slope, again, IIT said there could be a difference, but on the ipsilateral, that wasn't the case, and contralateral, no one predicted anything, and that was the case. So the second experiment is on curvature or location. So here, the idea is a stimulus is moving up and down next to the blind spot or not. And so next to the blind spot or below the blind spot, different location, same experiment. And the task is always to say, is it bound towards the right or left? And the idea would be that around the blind spot, it could be bent in one direction. Here the result is again no difference. And again, in the comparison with the predictions, IIT proposed that there could be a difference. They were medium sure about this. That wasn't the case. And let's move to the third and final experiment, at which we looked at the distance of two dots. And the dots could either be, the target could be outside of the blind spot, and the foil would be moving at different directions over the blind spot or not. And here, this whole experiment was either done on the above or below, or outside. So the lower one, both cases were outside of the blind spot. And the foil and target was compared in size. And so now this is the question. Is in this case where two dots are compared over the blind spot, is that perceived to be different or not? And again, who thinks the distance is different over the blind spot? Okay, of course you're intimidated now. Now there are only 4, okay? And who thinks there won't be any difference? Okay, you're the majority. However, the result, a clear effect. There's a real strong effect. So that's replicated in, that's in Glasgow and replicated in Toronto, and you have an effect. And the details of that is, I mean, it's predicted. So there's even a stronger effect on the contralateral eye, but in the non-predicted direction. Anyway, so IIT has a point. It says it will be decreased. And they scored here, and the predictive processing didn't. And there's a difference in bias, also in the contralateral. Again, that was clearly the case. So both of the curves are up, shifted. And then there's also a difference in slope that was predicted, but it went in the opposite direction. So IIT can score on the slope. And by this, we can come to the conclusion, but bear with me for another minute. So the 3 spatial judgments came to the conclusion that the extendedness around the blind spot, in the distance case, it's most consistent with IIT prediction, with a counterintuitive prediction that there's a size difference. The area was most consistent with the predictive processing, and the same for the location or motion curve. So what was different with the distance task? And so you could take the perspective that the distance is maybe the most sensitive one. It's really the one that's where the 2 dots are arching over the blind spot, where in the other case it's surrounding it, and so maybe it made it most sensitive. Or could it be something else? So up to this point was pre-registered, right? I mean, there's a clear score for IIT. So now Patrick Kavanagh, being Patrick Kavanagh, he said, you know, there's this thing about this vertical effect. And I feel a little bit uneasy about this. So vertical effect means these two lines, the vertical one looks a little bit taller, even though the same size. And the way we presented the stimuli, they're all pointing, they're at the same polar coordinates. I thought that's a very good way of doing it. But he said, why don't we try it in one different way? Because here we have more vertical effect, and here more vertical effect than here. So if we place the stimuli just like parallel to one another, we're testing the same hypothesis. So we quickly asked our theory leads, would you, if we do this change, would you still stick with your predictions? And all agreed, they had the same predictions. And so now, in the interest of time, I'm not going to ask you again, but the result, the effect is gone. So the effect is gone, and it is, so that's how it looked before the correction, and that's how it looks now. So doing proper science, you need to pre-register and not change your design. So IIT clearly won with that prediction. We also, you shouldn't do small numbers. So actually, you know, I said this is 14 and 22. By now we have the numbers more closer to 64. It's still in progress. But we did another control, or they did, actually Patrick's lab, and they replicated the whole effect by doing the non-parallel version more inwards, and you recover the effect. So, and this is done only by 8 subjects and not pre-registered, but I think quite meaningful. So, coming to the summary, now I think in the end it looks as if IIT didn't score on any of those experiments. However, I have a bit of the afterthought, and that is thinking about the vertical effect and the illusion in the first place could be something that might fall out of the retinotopic distortions that we have, the fovea being much closer and the periphery being coarser. But those are not predictions that came from the theory leads or that were suggested or pre-registered. But I feel a little bit uneasy to say, you know, predictive coding has nothing to say about these or less to say about the illusions, because if they are about minimizing the prediction error, you clearly should, you know, if you take a cookie this way or that way and you perceive it as being bigger, you should get a prediction error and you should adjust to that. I leave you with that thought. I did discuss it recently with, you know, Anil Seth, for example, and, you know, they have something to say about why evolutionary, you know, you might buy some just so mechanisms that compensate for, that buy in an illusion. So this is just to show you that these objects are perceived equal in size, and this effect is known for hundreds of years. I'm done. And I take questions. Yes?
Okay. Yes, there we go. Thank you. Thank you for the adventure. That was quite fun. I had a question that comes out of effectively from the first talk leading into the second in my own mind, which was that when you started with the hypothesis that the impact effectively at the earliest visual stages of processing, where you have this blind spot effect, it has an impact on the connectivity there, which IIT at that level might say, hey, okay, that connectivity should change subjective experience. If we think of subjective experiences occurring later in the pipeline, you could completely resolve that that whole through a different representational structure that actually accounts for that space. So I'm curious, kind of, I guess there's a limit to the level at which we're able to talk about the impact of this kind of study. I'm curious for you to talk about that, to hear from you about that.
Yeah, I mean, I proposed to Julio various ways of like filling in or top-down processing, which is more the thing I do as my day job for, to look in cortical, back projections and so on. But he wasn't interested in that at all because he said, "Oh yeah, of course. Once you go higher, you have more contacts and contacts. They do something and they add to that. But you have something. You have this first canvas of at which things are at a certain place, and then they do something. You can correct them, or they might fall, but that can come later. But to start with, you have this cause-effect structure of that phenomenon, the kind of space, and that is what he's interested in, where he's starting from.
Maybe if I speak up, so it's fine. So did you already have the results for the mice study, the deactivation? Can you spoil the results?
There are pilot results, and I will not comment on them. So we need to be a bit careful. So these are, pre-published data, but they're at a stage where we, as a consortium, kind of feel good about them. We have discussed them and so on. But the mice, there are many details, and I don't want to take any attention from those results.
So the reason I'm asking is because there you said you sort of experimentally deactivated neurons that were inactive. And there, of course, if that warps space, there's no argument against it. In the case of the blind spot, I can imagine that there's some idiosyncratic means to compensate for, the grid to begin with. I mean, obviously, sort of, Danoni knows IIT better than I do, but I could imagine there are some counter-arguments there. Whereas for the my study, I couldn't find any counter-arguments.
Yeah, so if you're interested, I mean, they are pre-registered, so the whole design is online at OSF, and that study is also at PLOS ONE, pre-registered, so the hypotheses are there. And there are technical problems with getting the mice to train and to respond, but the idea here is, you're stimulating a region and then you're cooling another area adjacent to that. Does that affect the overall weight percept of is it more left or right?
Great stuff.
And did I answer the question?
Yes.
Thank you. We need to move on.
Yeah. That's wonderful. So we'll move on to Steve Fleming next, who's going to discuss higher order theories of consciousness.
Okay, great. Well, thanks everyone for coming along. Thank you, Paul, for organising this session. I think one useful goal for the session today is to really, as Paul was advocating, show how we can do work at this intersection between what the CCN community are interested in and consciousness science. And I think Lars gave a lovely example of that. We're also involved in an adversarial collaboration, but ours is much earlier in the process, so I won't be talking about any details of those experiments or results yet. I'll mention it briefly towards the end of my talk. I'm going to talk about the following things. I'm going to explain briefly what computational higher order theories of consciousness are, and under these theories, the functional goal of consciousness is to solve what we call the reality monitoring problem, and I'll tell you about some empirical work we've been doing in our labs in collaboration with Nadine Dijkstra at UCL on how the brain might solve that problem. And I'll then also tell you a bit about an evolutionary story about the origins of reality monitoring based consciousness that I've been working on in collaboration with my philosopher colleague Matthias Michel, who's based at MIT. And I'll end briefly with a description of our adversarial collaboration ethos. So what are computational higher order theories? Well, computational higher order theories, broadly speaking, say that consciousness is the brain's way of keeping track of which aspects of perception reliably reflect the external environment. One way of thinking about it is it's our interface between perception and cognition. So in a more CCN way of speaking, we're conscious then of aspects of our world model that we can use as a secure basis for simulation and planning. Conversely, these theories proposed that we're not conscious of various internally driven aspects of the machinery supporting perception, decision-making, and so on. So the machinery of perception and motor control, things like we don't have direct access to the priors in a Bayesian scheme, working memory, replay, internal noise, and so on. These should be discarded because they're not part of the world model that we've built, essentially. So there's quite a close coupling between the idea of consciousness in these theories and broader predictive processing accounts. There's quite a nice intersection there. And one, I think, more unique feature of these theories is that consciousness is allied then with solving what we call the reality monitoring problem. So does a particular representation of the external world reflect the world as it is now, discarding all these other internal processes? And so this means then that computational higher order theories say that the problem with consciousness is, in a sense, solving this problem of reality monitoring. And the reason it's a problem for brains is because we know that we reuse perceptual resources to imagine and think about the world. This is an empirical feature of much recent investigation into internal imagery. So we know this is a review from Nadine and colleagues showing that there's nice overlap in, for instance, the ventral visual stream between what's going on when you're imagining things and when you're actually perceiving those same things. And that goes all the way down to the single neuron level. This recent study from Doris Sau's group showing that when you ask people to imagine simple objects, then you recapitulate the same neural population activity as when you're perceiving that object for real. So then this problem of reality monitoring then is, how does the brain know whether sensory activity is reflecting reality or imagination given this overlap? And this is the question that over the past few years Nadine and I have been tackling. So Nadine was a brilliant postdoc in my group. She's now gone on to start her own lab at UCL addressing these very questions. So if you're interested in this line of work, then please go and speak to Nadine. So the kind of thing we've been doing is experimenting with the imagination in the lab, looking at how people are able to imagine low-level visual stimuli and then tell the difference between real stimuli and imagined stimuli. So we might give you a patch of flickering noise like this and ask you to imagine, for instance, this left-tilted grating appearing within the noise as vividly as possible, as if it were really there. And we can then ask you questions about the vividness of your experience, whether what you saw was real or imagined, and so on. So let's all try this together now. If you just have a look at this template on the right-hand side, and then I'm going to show you a patch of flickering noise. I want you to try and imagine that template as vividly as possible in the noise. Okay, ready? Wah! Okay, go. Okay. Was a real stimulus presented on the screen? Yes. Yes, okay. So we asked people this question. Now this was relatively straightforward because towards the end of that flickering noise we did ramp up a real stimulus, but in the experiments that we've been running we titrate these real stimuli down towards threshold, and then you can probably get a sense it's going to be quite a hard thing to do, right? To tell the difference between whether what you're seeing is imagined or real. So in one of the first experiments we ran on this topic, we gave people a few trials of imagining these low-level stimuli, asking them how vivid their imagery was, and then unbeknownst to subjects on our final critical combination trial, we faded in a real stimulus just like the one that you saw there. And importantly, there were two different conditions. Either that real stimulus could be congruent with what we're asking you to try and imagine, so the same orientation, or incongruent, so the orthogonal orientation. And then we can ask them this final reality monitoring question: was there a grating actually presented on the screen, or was anything you saw just imagined? And what we found in the data was that perception and imagination were intermixed in surprisingly extensive ways. So when your imagination is congruent with the orientation of the real stimulus, you are more likely to say that there is actually a real stimulus out there. It's almost like imagination is adding a bit of evidence for your inference on reality. But also vice versa, when you judge things as real, these solid bars here, those are also the trials on which you say your imagery was particularly vivid. So what's going on here? Well, one way we started thinking about these data is that the brain might actually be using the vividness of this internal experience as a cue to decide whether something is real or imagined, given that one of the salient differences between imagery and perception is the vividness or amount of detail in your experience. This is not a new idea. This goes back to David Hume and in his treatise on human nature, saying here that the idea or imagination of red, which we form in the dark, differs only in degrees of intensity, not in qualitative nature, from the perception of red that strikes our eyes in the sunshine. So this idea of imagination and perception existing on a continuum. So to try and quantify that more formally, we developed a simple computational model. This is an extension of signal detection theory where we now drive a common population, not just by the input, but also by internal imagery. The idea is that these signals are getting intermixed, and then the subject is comparing the intermixing of these signals against a threshold. In the case of perception, these signals are relatively strong. In the case of imagery, they're a bit weaker. And then you can compare this against what we call a reality threshold to decide whether, if it's strong enough, then it's real. If it's a bit weaker, then we decide that it's imagined. So the nice thing about writing down a model like this is that we can simulate what we should expect to see in the empirical data in this kind of experiment. So just a reminder, this is what the data pattern we saw. And the model simulations do a nice job of qualitatively capturing this effect with just this very basic intermixing between perceived and imagined signals. Now, this was somewhat of a post hoc explanation. We developed the model after seeing these data on the right-hand side, but we can also generate novel predictions, out-of-sample predictions for new experiments. So Nadine came up with this idea of asking people to still make the reality judgment at the end of the experiment, but now not presenting any stimulus at all. And the model suggests that what should happen in this no stimulus experiment is that you should see people judging something as real when their imagery vividness happens to be particularly strong, because that's driving you over this reality threshold. And that's exactly what we see in the data when we ran that second experiment. So since then, we've gone on to explore this effect in various ways. We can look at it swept across a full range of input contrasts. The prediction there is that congruent imagery should lead to a baseline shift in the probability that you judge something as real, and that's exactly what we find. We see that congruent imagery shows a leftward shift in the psychometric function here. And we've also investigated the extent to which people have metacognition or insight into how imagery is affecting your responses. It turns out that participants don't really have much insight into this. We look at how confident they are in that reality judgment. They're just as confident in the illusion of reality in the congruent imagery condition as they would be if a real stimulus were actually presented. So it seems like this intermixing is happening relatively automatically, and once it's intermixed, it's hard for people to tell the difference between perceived and imagined information. So most recently, Nadine's ran this paradigm together with functional MRI to look at the neural basis for distinguishing reality from imagination. We relied on simulations of this simple model to try and develop some qualitative predictions for what we should see in the imaging data. And I won't talk through all the details here, but essentially we can simulate what we should expect for the magnitude of this internal intermixed signal, this reality signal, as a function of different cuts through the experimental design, as a function of stimulus, the person's response, how vivid their imagery was, and so on. This gives us a nice, rich qualitative pattern that we can use to try and look for brain regions that show this signature of the intermixed signal. And what we found was that in the bilateral fusiform gyrus, so in mid-level visual areas, we saw that all these signatures of this intermixing were obtained. This is pretty striking, we think, because these stimuli are relatively low-level gratings. And yet the intermixing we see between perception and imagination is in mid-level visual areas, not in early visual cortex. We also were able to look for neural correlates of the reality threshold. The way we can do that is by comparing bold signal that is better explained by a binary regressor for the reality judgment than a regressor that's tracking continuous variation in imagery vividness. And when we do that contrast, we see a network of prefrontal areas, particularly the anterior insular and the posterior medial frontal cortex, also the striatum. And in particular, within this network, we see that the anterior insular shows strong and sustained coupling with this region of the fusiform gyrus here. So one interpretation of these data is that essentially the downstream prefrontal areas are monitoring the strength of this intermixed signal to decide whether something is real or not. So one way of thinking about this then is that essentially you have this intermixing going on in the visual system, and that you need some downstream readout of the strength or reliability of that signal to be able to decide whether something is real or not. Now, clearly this is not the only factor that makes a difference for whether we decide something is imagined or real. Things like how much control you have over your imagery, how much time it takes you to imagine something, the context you're imagining it in, all the factors that we expect should affect this reality judgment. And these are factors that Nadine's actively investigating in her new lab. So do talk to her if you're interested in that work. Now, I think this solution to the reality monitoring problem that we're proposing in this empirical line of work is nicely allied with theoretical proposals that's coming from the consciousness science literature. So Hak-Quan Lau's proposal here is known as the perceptual reality monitoring model. And the idea here is very similar to the model I just showed on the previous slide. The idea that a higher order discriminator is attempting to distinguish between internally generated signals and externally generated percepts. And this model, Hak-Quan argues in his 2022 book, provides a psychological basis for conscious experience, because under PRM, conscious experience is the process of trusting signals for the use in the service of cognition. Conscious experience is what we call external reality. We can formulate that within a predictive processing framework. This has been a line of theoretical work in my group. This is what we call the higher order state space model. Very similar flavor. The idea here is that the higher order states in the predictive processing framework are monitoring whether a first order world model is reliable enough. The way it does this is it marginalizes over all the content in the first order model. So the idea is that the top of this model is actually pretty lean and not very rich. It's basically just performing this reality monitoring operation. And it's saying if the first order world model is reliable enough, then we can use it as a basis for further cognition, simulation, planning, and so on. With Nadine, we've recently been expanding this model out to be slightly more sophisticated than just a single layer of monitoring at the top. Here we have the idea that not only are we monitoring the strength of the first order representations, but also their precision. And this account can, the idea is that the monitoring of precision is underpinning our sense of reality. That allows us to start modeling why people are able to generate internal imagery that is perceptually strong but not confused with reality. And this is a recent preprint if you're interested in checking out the details of this. This actually means that this kind of framework is coming very close actually to the proposal from Hak-Quan Lau. There's not really any meaningful difference. It's just that we're trying to operationalize it within a predictive processing account. So now I just want to switch to talking about this work we've been doing with Matthias Michel on evolutionary perspectives on consciousness. And we've been developing this notion that reality monitoring might shed light on the origins of functions of conscious vision. And more broadly, what we're trying to do here is ask, what is consciousness for? And I think this is a useful question to ask because most theories of consciousness treat the brain kind of as an endpoint. Something becomes conscious, and there's some kind of property of the system that generates this difference, like recurrent processing, like global broadcast, and so on and so forth. But in all the theories we have, really, there's been limited consideration of the functional goals of consciousness, what is consciousness for. And that's quite different to other areas of cognitive science. We have this implicit assumption that we can understand the internal operations of the system in terms of decision-making, memory, perception, and so on, in terms of the functional goals. And this piece has been missing in consciousness science, I think. And one way of thinking about this is within Mars' levels of analysis, where a lot of our theories are situated more at the neural or algorithmic level, and we know pretty little about the functions or goals of consciousness. And this is where I think the CCN community has an exciting role to play here, because we're really used to thinking about how to cross these different levels and how to think about this functional level as constraining algorithms and implementations. And this, I hope, would have been music to the ears of the late Daniel Dennett, who was always fond of asking what he called the hard question of consciousness as opposed to the hard problem. So he would always say, once someone posed him an explanation of the difference between conscious and unconscious states, he would say, okay, but then what happens? Why is it, what's the point of that difference that's been set up there? So with Matthias, we've been very inspired by this work by Malcolm McIver, who's a roboticist and evolutionary biologist, who has been working on this notion of sensory horizons. So a sensory horizon is how far you can sense beyond yourself. And McIver proposes that the water-to-land transition is a key evolutionary juncture for this massive expansion in visual range, because the physical properties of water mean that you essentially cannot see very far. And under these limited sensory horizons, then you are forced into a mode of behavior which is dominated more by faster sensory motor reflexes, because anything that's impinging on your sensory volume comes quite late in time. Whereas as soon as you get this terrestrial visual scene, you have a massive increase in sensory range, and then it becomes adaptive to have these slower timescales of sensory motor action control. We get the luxury of being able to think, essentially, based on what we're perceiving. So the general idea then in the case of vision is that if you have a large sensory horizon, you have the luxury of cognition, you can take your time to plan and so on. Imagine you're driving down a road and you can see way down the road and an animal walks out in front of you, but it's still way, way down the road. You don't panic, you can kind of slow down, think about where you're going to stop and so on. Contrast that with this situation where your sensory horizon has been limited by driving down the road in the dark. Now imagine a deer jumping out in front of you. You won't have any time for perception to shape planning. You're just going to have to act in reflex mode. So the idea is that under these shorter sensory horizons, the faster reflexive habitual actions are guiding behavior. And as Paul mentioned, we consider these as largely unconsciously driven. And one of the reasons why we think these are largely unconsciously driven is because there's been lots of nice work on the speed of conscious vision looking at postdictive phenomena. I'll show you one of these in a second, where the window of integration in conscious perception has been quantified using various different techniques. And it suggests that the speed is kind of towards the right-hand end of this gradient. And if conscious vision is relatively slow, then that suggests it can play this functional role in cognition over larger sensory horizons, but it's less useful for online control of action. I won't talk through the details of this study, but I highly recommend it from Michael Herzog's lab. It shows using these Vernier offset paradigms how there are surprisingly long windows of integration in conscious perception. The take-home message here is this one, basically, that we kind of have the intuition that what we're seeing is guiding our actions, a bit like you might have the intuition that the Formula One driver is making the decision to go on the basis of conscious perception, but that's really a kind of postdictive illusion that we're building these conscious models for something else. It's still very useful to have them, and I'll tell you why we think it's useful, but they're not actually controlling the online response. This also fits in with work, for instance, from Mel Goodale and David Milner, suggesting that the online control of action might be driven largely unconsciously, or at least more unconsciously than we often like to think. So the proposal in the paper with Matthias is the longer range visual horizons afford the time for visually guided planning. This capacity is supported by the slower speed of conscious vision. Online action control is, in contrast, guided largely unconsciously, and that the emergence of this capacity to use perception in the service of internal planning, simulation, and so on required the development of these reality monitoring strategies. And in particular, it required the development of reality monitoring over time, because animals face the need to plan in the here and now. And the problem is that here and now is always changing. The predator may be here now, but wasn't a few seconds ago. And that creates this tension between engaging goal-directed planning within a stable model of the world. We need it to be reliable enough in order we can plan, but we don't want to wait around for so long to make it really nice and precise and detailed if we then lose dynamic coupling with a constantly changing environment. And we propose that the temporal window of integration of conscious perception is functionally resolving this tension. It's allowing us to simulate within what the world was like in a kind of 300 to 400 millisecond timescale. And this then poses questions about how is reality monitoring extended over time? Can we extend out these kind of computational higher order models over time and start looking at the dynamics in relation to this window of temporal integration? And that's something we're actively pursuing in the lab. So just in the last 2 minutes, I will just mention this adversarial collaboration. We're just getting started at the moment. This is part of this suite of adversarial collaborations that Lars has already introduced, funded by the Templeton World Charity Foundation. Ours is called Ethos, Empirical Tests of Higher Order Theories of Consciousness. This is testing this broader class of higher order theories. I've already talked about how higher order theories suggest that there is a particular role for higher order monitoring in conscious perception, and that first order representations are not on their own sufficient, and instead consciousness is constitutively dependent on some kind of monitoring. But what's interesting is that different variants of higher order theory propose different types of role for this higher order monitoring. And these different roles are largely computational rather than anatomical. So the front versus back of the brain debates that Paul mentioned earlier, I view these more as a starting point, as kind of rough placeholders for first order and higher order contributions here. But really, we're trying to contrast computational level theories and do that using the tools of cognitive science. So Ethos is trying to compare different theories, including some of the ones I've mentioned already, like Hoss and PRM, along different axes of disagreement. So different theories propose that higher order representations are richer or sparser, and whether they can misrepresent their first order targets and in what way. This is being pursued in the same style of science that Lars mentioned, or pre-registered with multi-site replications. We've got a large multi-site team across UCL, Brussels, UC Irvine, Northeastern, Sussex, Boston University, and involving contributions from theorists Hak Kwan Lau and Richard Brown as well. There's 3 different experiments within the collaboration, and we're gearing up in the next few months to be making public the protocols we're going to use for these 3 experiments, but they're combining psychophysics, brain imaging, and hypnosis to look at tests that can distinguish between these different predictions of the different higher order theory, really kind of zooming in on what is it about these higher order states that might enable this difference in conscious experience. So it's a somewhat unique adversarial collaboration because it's really testing within a family of theories. If higher order theories are just completely on the wrong track, then we can't really adjudicate that within our collaboration, but it does allow us to develop empirical tests of the different commitments of the different models. I'll just put a box around this one because this is setting up, hopefully, some of the things that Megan will tell you about, which is using neuroimaging to try and test between Hoss and PRM in terms of the neural code that might underpin this kind of monitoring signature. And I'll stop there and take questions. Thanks very much. There's one there, yeah.
Yeah, thank you. there was one thing that I didn't quite understand in the first part of your talk. So I understood you saying that the contents of consciousness are basically my model of reality, so what I take to be the real world. But then, as you pointed out, when I imagine something, that's also conscious. So how does that go together?
Yes, no, great question. I think there are different ways of thinking about this. So one line of evidence for that question is on studies of aphantasia. So people have been interested in whether people who don't have conscious imagery, what can they do functionally? And it seems like they can do quite a lot of things functionally, including, say, visual working memory, mental rotation, and so on. So one way of thinking about this is that essentially the conscious imagery is, in some sense, the spillover of internal activity that we're using in a functional way in terms of simulation and planning into consciousness. But it's not got any functional role by being conscious. That's a line I favor. I know Nadine has slightly different views on this. But yeah, so it's a really interesting question. Like, does being conscious of your imagery tell us something about the function of consciousness, or is it kind of a red herring? Yeah. Yeah.
Hi. I have a question. So I'm having semantic confusions, let's say. So you say functions of consciousness, but then we use consciousness as an adjective a lot, like it's conscious vision. So is it more functions of some process that we associate as consciousness, or consciousness as a, I don't know, like a having a characteristic, let's say, measure inside some dynamic process, like gravity. Gravity would have a gravitational constant. That's a completely different thing. That's a force.
Sure.
Whereas an attractor state in a dynamical system would be a description of what's happening. So so from the first talk and this talk, I heard mostly it as a description, like there is something happening and we call it conscious, but then we are talking about the function of that thing, right, and not really about consciousness. Like, could you?
I think it's a great line of questioning, and there's so much to say about this. I think it really exposes some deep divisions in the field of consciousness, how people think about what consciousness is. And this differs across different ways of theorizing about it. So really what you're asking is, is there something intrinsic about consciousness? Is it fundamental in some way? And that's what philosophers call the kind of manifest way of thinking about consciousness, that once you grasp it, you realize that from the first person experience, there's some essence that needs to be explained based on some fundamental property of the system. Now, these approaches, the ones I was talking about, take a slightly quite a fundamentally different stance on that, which says that once we have, it's a functional perspective, once we have explained the functions, then there's not anything additional left over, that it's not necessarily the functions of consciousness, it's functions for consciousness. The reality monitoring story is probably the strongest one in that respect, because it says that essentially the computations that may be supporting something like reality monitoring distinguish between what is real and what is internal. That just is the basis of what we are calling conscious experience. So then it becomes more of a descriptive account. We have these folk psychological concepts, and there's a cluster of functions that we say, okay, that is what we're calling consciousness. Once we've accounted for all those functions, then essentially the research program is over. And that's quite distinct to a metaphysics which says, no, there's something fundamental, right? And I think that's more of a philosophical question. Science is not necessarily going to be able to discriminate between those two. Yeah. Good? Okay.
That's wonderful. So for our final talk, we'll hand over to Megan Peters to look at the distinction between first-order and higher-order theories. Over to Megan.
Awesome. Okay, so yeah, we'll talk a little bit about the adversarial collaboration that Steve just mentioned, and then I'll zoom out and talk about another one that's much further along and actually has some results to share with you. And then at the end, I think I'd like to set us up for thinking about not only where we go from here, but also how the CCN community can help, and how what we're talking about in this community event really fits in with a lot of what CCN is already doing and how you all have been thinking about this so far. Okay, so I'm just going to jump straight into it. We've introduced the idea of first-order theories and the idea of higher-order theories. So I'm just going to tell you a little bit about our plans for that branch of the Ethos project that Steve put a box around at the end, which is really questions about if higher-order theories are right, what are the dimensions or dimensionality of the higher-order representations, and how do those subserve the reality monitoring function? And also, as Steve mentioned, this is part of a massive collaboration led brilliantly by Steve and Axel with a lot of wonderful support from Sarah, so I want to call her out especially. And then the branch that I'll be talking about is led by myself, Jorge, and Nadina, with a lot of wonderful support from all of the students, trainees, and postdocs. Okay, so we're asking in this particular branch, which variant of higher order theory is less wrong? And I'm using the words less wrong really purposefully here because none of these adversarial collaborations is designed to say which theory is right. It's just to say which one doesn't lose terribly. And so none of these is going to prove any one of the theories correct. It's just going to say which one didn't completely suck. So what we're looking at here is specifically an arbitration between perceptual reality monitoring and higher order state space theory. And the critical difference between these theories for the purposes of this particular branch of the adversarial collaboration is essentially whether they whether they use vividness as the reality monitoring signal or not. So higher order state space theory, as Steve mentioned, says that vividness is kind of all you need, that if something is more vivid, then it is more likely to be real, end of story, and that is what the higher order monitoring mechanism cares about. But perceptual reality monitoring theory posits that maybe there is a separable, maybe not orthogonalizable as in this, this particular diagram, but nonetheless separable dimension along which reality monitoring might occur that is different from vividness, conceptually and maybe computationally. And so the idea here is that you could have a very vivid imagination experience. It is possible to have a very vivid imagination experience that you would never confuse for reality. And so it might be that in the experiments done so far, we just haven't had the power to tease these two possibilities apart. So what this project is going to do is use a perception and imagination paradigm. We put people in the MRI scanner, we ask them to look at stuff, we ask them to imagine stuff, and we manipulate the images, as you can see in this diagram here. Oops, where's my mouse? Okay, yeah, we manipulate the images during the perception trials such that we're trying to match the distribution of vividness as much as possible across perception and imagination. So we have to degrade your perception to kind of bring it closer to the best imagination that you could have. And then we're going to take the signals that come out of the MRI, the multivoxel patterns, and we're going to be doing kind of a searchlight approach, but also a targeted ROI analysis, coupled with a computational technique, which some of you might be familiar with, called domain adaptation. So this is a machine learning technique that is meant to bring into alignment two different target domains, the data distributions from two different domains. So you can think about this as all of the multivoxel patterns that come out of the brain when you're looking at stuff, when you're perceiving, versus all of the multivoxel patterns that come out of the brain when you're imagining those same objects. So if I say, look at a chicken or imagine the chicken, your brain is going and do it over and over and over again, you're going to get two different distributions, but the statistical approach here through domain adaptation is going to try to correct for any differences, distributional differences between those. The goal here of doing this alignment across perception and imagination to bring those into statistical alignment with each other is that we're essentially collapsing the reality monitoring dimension. We're finding the statistical signals that that reality monitor might be looking at from a higher order perspective in the brain. And then we can ask, is there anything left over? Is vividness still there? If I've collapsed the reality monitoring dimension, and I've destroyed the vividness signal, I can no longer use any approaches to find that vividness signal anymore, then maybe the higher order representations that I've found do indeed say that reality monitoring and vividness are the same thing. If there's vividness still left over that I can decode from those now statistically aligned patterns, then maybe perceptual reality monitoring is onto something. So we're going to be relying on some methods and toolboxes that have been developed by David Soto's group in Spain, and then using this domain adaptation approach to do this. I don't have any results to show you. It's just this is what we're doing. And so we are now working on the open and reproducible pipelines here, and we'll have a poster at SFN about this, led by my postdoc, Ali Eklassi. Okay, so, and this is just one branch of the Ethos project, and so we'll go ahead and move on to some data that I have to show you from the other adversarial collaboration that I am a part of, also funded by the Templeton World Charity Foundation. And this one is supposed to bring together some of the conversations that we've had today. So we heard a lot about first order theories, and there's lots of different variants of those. And then we heard about higher order theories. So this adversarial collaboration, which is also a massive group of people, the kind of overseers of the project are Ned, Dave, BU, and then another branch of the project is led by BU and Jan. And the work that I'm going to be talking about today is co-led by myself and Rachel Dennison, with massive contributions on the psychophysics and modeling sides from Karen and Brian. And then the MRI components that I'll briefly introduce are also led by Michael and Emil. And the results that I will talk about today are actually up as a preprint. So if you're interested and you want to find out all of the details, you can not only go look at the pre-registration that we have up on OSF, but you can also go and look at the preprint and all of the 50 pages of supplemental material that it also includes. Okay. All right, so the purpose of this entire adversarial collaboration here is to ask, are first order representations sufficient to explain subjective experiences? And so as Steve mentioned, this is kind of beyond just the back and the front of the brain. This is really about the computational nature of these types of representations and these types of signals within the brain. So higher order theories say that sensory signals underlie objective performance, so it's potentially unconscious. And only those higher order signals that might be kind of looking at the first order signals, those are the ones that track the subjective experience, the vividness that we have, that we experience about our perceptual processing. And so these higher order theories essentially then say that there's maybe something that's kind of up generally in this vicinity in the brain, but again, it's not about anatomy, that's watching those first order representations and then making judgments about them. So that these are representations about representations, which themselves are about the external world. And the contrast then is those first order theories, and the theory version that we're looking at in this adversarial collaboration is the local recurrency theories that are primarily led by Victor Lema and his colleagues. And those versions of first order theories say that sensory signals, in this case, the strength of recurrent processing or recurrent feedback in early to kind of mid-visual cortex, that those signals, that whether they're strong or weak at any given moment, that is sufficient to explain both your objective performance capacity and your subjective experience, the vividness with which you perceive the world. And typically, these kinds of approaches will use as empirical evidence supporting the local recurrency theoretical constructs that if I show you this image here on the left, all of you, I hope, will see like a little square kind of popping out from the background. But if I rotate this little square 90 degrees, it completely disappears into the background. Or if I rotate, in this case, the background 90 degrees, the little square disappears. And so the idea here is that this kind of pop-out effect that is conscious is driven by the local recurrency, the feedback that happens in earlier visual cortex. So you can measure, using neuroimaging approaches, electrophysiology, EEG, or even MRI, the level of the strength of the local recurrency by showing people a bunch of these things on the right, and then showing people, or monkeys, a bunch of these things on the left, measuring the brain activity that goes with both, and then subtracting. So the idea is I subtract off the feed-forward sweep, which is identical between the two images, and then what I'm left with is the strength of the feedback on a trial-by-trial or condition-by-condition basis. Cool. All right, let's do that. Let's measure the level of first-order recurrency and see whether it tracks subjective experience. If it does, first-order recurrency theory wins or doesn't lose. And if it doesn't, then it does lose. Easy. That's the end. No. There's a problem. And the problem is that, like we've kind of seen throughout the talk so far, the better you are at seeing the world and operating within that world, the more subjective experience you typically have. And this is true in basically every study that has ever been done on subjective experience. You say, oh, you have a detection D prime that's higher and you saw it more vividly. Yeah, well, now they're just perfectly correlated. So I don't know, if I don't control for that, whether I am measuring objective performance capacity and its neural correlates, or subjective experience precisely, uniquely, in isolation, and its neural correlates. Make sense? We can see this really carefully, or really easily, in like attentional manipulation. So if I make you attend to something, you're going to do better at telling what that thing is, or where it is, or you're going to have a stronger ability to detect that stimulus. So, contrast sensitivity is improved, spatial resolution is improved, and you also think that it's brighter. You think that it's louder. You think that it's bigger, those kinds of things. So they're perfectly correlated. So we have to find a way to control for that, to control for the objective performance. All right. Turns out there is still hope, though, and attention may, in fact, be the key, because attention does something very strange as long as you account for the benefit that attention gives to performance. So what this means here is that if I account for or control for performance, if I match performance across attended and unattended conditions, that attention seems to counterintuitively lower visibility ratings, especially out in the visual periphery. I'll unpack this a little bit. What this means is that, if you're not paying attention to something, your accuracy does indeed go down. Okay, you get worse at some task. But your subjective experience does not go down enough to account for how much worse you actually are. Okay? So both went down, but one went down more. So they start to decouple. This is a phenomenon that's known as subjective inflation. It particularly occurs out here in the visual periphery when you don't have a lot of cones at your disposal. And so what we can see is that for this unattended visual periphery, our phenomenal experience can be stronger, sharper, or more vivid than the accuracy of sensory processes would suggest that it should be. So we're going to use this to start to pull apart subjective experience and objective performance. And that's great. The problem, though, is that up until this point, the robustness of this subjective inflation phenomenon has been a little suspicious. So it's been reported in the literature in a few experiments, but the degree to which it generalizes, especially to some of those figure ground stimuli that we would need to use in order to get at the first order recurrency signal, that's never been done before. So the first thing we need to do is make sure that this isn't just some cute response bias effect, that this is really real, that this is actually a dissociation between subjective experience and objective performance. And so previously what's been done is that you'll titrate the strength of a particular stimulus. You'll do a thresholding approach, and you'll say, okay, in one of the in the unattended condition, I find the level of contrast in my Gabor patch that gives me 75% correct detection accuracy, and I do the same thing in the attended condition, and so I match performance perfectly, and then I go about looking for subjective experience differences, which means I had to really mess with that stimulus a lot in order to get that performance to match between attended and unattended conditions. And then the other problem here is, what if 75% correct isn't like the biggest effect size I could get? What if, down here near 50% correct, I would have gotten a much bigger effect size in the subjective experience, or a much smaller effect size? I don't know if I'm just doing thresholding. So what we're going to do here is we're going to start by developing a new analytic approach, which we're calling introspective psychophysics, to try to get at the actual entire range of the relationship between objective performance capacity and subjective experience across attended and unattended conditions. So traditional psychophysics, as we've seen today already, and I hope most people in this room are familiar with, would be finding the quantitative relationship between stimulus properties that are out there in the world and something that is related to your perception, your objective perception of that stimulus. So your orientation discrimination capacity, your judgments of which thing is heavier, that kind of thing, which thing is brighter. So what we're going to do is we're going to take the entire thing up one level, and we're going to find the quantitative relationships between objective performance capacity and subjective experience across an entire range of objective performance. This way I don't have to pick just one thing to threshold at, I can just do the whole thing. And then I can look for not just shifts up or down or left or right in my psychometric function, but changes in its shape. And that will also help me understand whether this attentional manipulation has changed the relationship between objective performance and subjective experience in the target way. So doing this will allow us to isolate not only the magnitude of a shift, but what it actually did. Okay, so what are we going to do to test the robustness and generalizability of subjective inflation under this introspective psychophysics kind of regime? We're going to use two different stimulus types. First, we'll start with the contrast-defined gratings. These are the standard thing that has been used by every visual scientist ever to look for subjective inflation. But critically, we're also going to use these texture-defined figure ground ovals because we're going to need them later to find that local recurrency signal. And we're going to do this not only at a near detection threshold, which is where subjective inflation has primarily been found before, but we're going to do this all the way across an entire range of performance capacities, an entire range of stimulus strengths. So we're going to do two stimulus types by two different kinds of experiments. One that's a detection experiment all the way down here at the visual threshold level, and one that's then up here where everything is super threshold, everything is relatively easy to see, but we're looking at changes in the relative vividness or relative subjective strength of the experience. Okay, all of the experiments then look something like this. We show you a fixation cross, then we show you a pre-cue here that says pay attention to one of the four quadrants on the screen, where we will then eventually show you a stimulus out here in the visual periphery. Most of the time, this pre-cue is valid, which means it says pay attention here, and then later respond here. And I'll tell you something about that response in a second. But most of the time it's valid. Sometimes it's invalid. Pay attention here. Just kidding, actually respond to this one over here. And then sometimes we have some neutral trials as well. So this is our attentional manipulation, central pre-cue. All right, the targets then show up, and then you have to respond. What are your responses, and what do the targets look like? Okay, in our detection experiments at the visual detection threshold, the task is to say, what is the response cued item? Was it tilted left or right from vertical, if it's a Gabor patch? Or was it a vertical or horizontal oval, if it's those little figure ground stimuli? And you have to say both an objective and a subjective judgment at the same time with a single key press. So you say whether it was left or right from vertical, and also whether you saw it or not. Like, did you subjectively experience this stimulus or not? We actually have 3 levels, but I won't get into that here today for the sake of time. And then we also have the suprathreshold stimuli. So now everything is easy to see. There aren't like half of the trials where it's not really there. It's not a detection experiment anymore. But the task is basically the same. Was the thing tilted left or right from vertical, or was it a vertical or a horizontal oval? But now the subjective judgment is about whether the experience of seeing this thing was stronger or weaker than a reference stimulus that we taught you previously. We spent 10 minutes saying, like, here's the reference stimulus, here's the reference stimulus, and then you have to just say, judge whether it's stronger or weaker than that reference. Okay, so what did we find? Results. Turns out subjective inflation is incredibly robust across everything that we did. And by the way, I didn't mention this here. There's 120 people in the data I'm about to show you. Each person has 6 hours of data, and this has been simultaneously replicated across my lab and Rachel Dennison's lab at Boston University. All right. So first, let's look at some classic psychophysics curves. On the x-axis is contrast. On the y-axis, on the left-hand column, is percent correct left or right tilt, or vertical horizontal oval. On the right-hand column here is the percent of time you said, yes, I saw the thing, or yes, it was stronger than the reference in those second types of experiments. And so then you've got your 4 experiments in the 4 rows, and what you can see across all of them is that in blue, when you do attend to the thing, you are better at the task faster. You need less, effective contrast or effective strength to do the task well. And when you don't attend to the thing, you really kind of suck at the task. Makes sense. And your subjective experience kind of qualitatively goes along with this. When you do pay attend, you think you see the thing better. And when you don't pay attend, you don't think you see the thing better. But remember, the key to subjective inflation is not whether you did worse but you thought you saw it better. It's whether you did worse when you're not attending and you think you see better than you actually kind of could relative to how well you could actually do the task. So the critical factor here is taking the y-axes of these 2 plots and sticking them against each other. And now what we can see is that red is always above black, is always above blue. So what this means is that when you do not attend, yes, you get worse at the task. You get massively worse at the task. But your subjective experience does not go down enough to account for how much worse you got. Okay, so to quantify this effect, we're going to take kind of the area under these curves. That's what this little shaded region is. We're just going to integrate under these curves and say how much subjective experience did you have across a matched range of objective performance capacity. So this is like area under the curve. Do some integration and plot the result as a bar plot. And now we can really see red, black, blue across all of them. All of them. So, incredibly robust. In every experiment, the unattended subjective experience outpaces the attended subjective experience once we account for the difference in performance capacity. All right. Did we disprove first-order recurrency theories? No. All we did was create a behavioral paradigm that now robustly dissociates these things. But that means that now we can actually measure those first-order recurrency signals in the scanner and figure out whether they go with objective performance capacity or subjective experience better. Because they can't go with both equally because they don't perfectly correlate with each other anymore. So we do the thing in the scanner, same experiment. I'll just show you here some pilot data showing that, yes, we can find that first-order recurrency signal in retinotopically mapped areas of early visual cortex. It's got this kind of interesting center-surround organization. I'm not going to show you the data here because we don't have the data collection finished yet, but the idea here is that now we're going to say, does figure ground recurrency go with subjective experience or objective performance better? And if it does go with subjective experience really well, then first-order theories pass. They don't fail, but if it better explains the objective performance capacity, then they might be, in trouble. So our pre-registered number here is 30. We'll have 6 hours per person plus retinotopy, and we're about 75% complete, so we're almost there. All right, in the last 3 minutes here, this is one half of this adversarial collaboration, which we don't have a cute name for, so we're just calling it FOHO for first order, higher order. And then there's another half that BU and Jan are running as well. Okay, in the last 2 minutes here, I will tell you then to wrap up though. I've talked about first order, higher order. We've talked about first order, higher order. Is this the only game in town? No. There's a whole zoo of these theories. And they don't necessarily just fall into these various different camps. A lot of them subscribe to what it's called computational functionalism, which is the idea that a system that has the right kind of computations, as we heard in the first talk, and actually throughout several, a system that has the right computations will become conscious. And so in this paper that Steve and I were lucky enough to contribute to, we went through a bunch of these different theories, and we kind of decomposed them into their constituent parts, and then said, to what extent do current artificial systems have the ability to show these kinds of kind of checklist marks. So here's the checklist that we came up with, that we decomposed these various theories into the necessary and sufficient computations that give rise to consciousness according to each of these theories. We didn't pick one as the right one, we just said, could artificial systems do this, and do they do it now? And so the idea there was that if there's an AI system that ticks more of these boxes in this cute little checklist, that maybe we have a higher subjective degree of belief that it might instantiate consciousness. But that's, again, about our belief that it might have consciousness, not like an objective ontological truth. Okay, and then the last thing that I'll mention, which I think is relevant for this community, is that, of course, CCN and in general, most of the people in this room are really into education. And so if we want people to learn how to do any of these things right, not just these particular theories, but any of the theories that we've been talking about today, or any of the constructs that we think might give rise to the functions of and for consciousness, we do need to train them to do it right. So I built the last day of our newest course at Neuromatch to be about consciousness, basically. And so with massive contributions from largely Steve Fleming and Guillaume Dumas, who built some tutorials in Python. Everything is reusable, remixable, it's all free. Go ahead and look at it. So if you're interested in learning how to make some of these theories go, you can actually go learn how to do it with these. But ultimately, what we're talking about here is building a giant community who can contribute in a very practical way to consciousness science, and CCN is a huge part of that. So if you go do this kind of course, and then you learn how to do some of this stuff, you can then also contribute to the theories behind the science that we've been talking about today. And so we've given you an introduction to several of the adversarial collaborations that are funded by the Templeton World Charity Foundation, but this isn't meant to be an advertisement just for them. This is also meant to be an advertisement for CCN. So as you all know, the Generative Adversarial Collaboration Project, which I was lucky enough to help co-found in 2020, has now had 17 GACs, or GACs, depending on how you want to pronounce it. And these are not open from the point of pre-registration on, these are open from the very beginning. So go and get involved in how to arbitrate among not just theories of consciousness, but theories in general. And if you'd like to read a little bit about the GAC project and how it kind of came to be and what its goals are and how it's kind of open from the beginning, then please go read this. But then the GACs are all kicking off this afternoon. So if you like the idea of adversarial collaborations and coming up with like the experiments that will critically find the pinch points between theories or hypotheses, that'll be great for you. Okay, so that's all I'm going to say. Please join us. Oh no, that's terrible. Why did it break? Please join us for consciousness science. Oh, I have a really cute GIF. Okay, never mind. Please join us for consciousness science, and please join, adversarial collaboration kind of projects in general. I hope that you've had some fun and learned something today, and we're going to have a panel discussion now. Thanks. But any questions for me too? Yeah. I don't know why it broke. Why did it turn off?
So have we got a couple of questions for Megan? And I'll also invite Steve and Lars to come up to the front in preparation as well.
No questions for me.
Yeah. Oops, sorry, we've got...
Yes.
Yeah, I was just wondering how does the first order theory survive just the demonstration that you can dissociate? I would think that a prediction of that theory would be that you can't dissociate subjective strength and performance.
Yeah, that's a really good point. So the predictions tables, which I didn't show, are that discovering that subjective inflation is incredibly robust would be a weak challenge to Victor's theories, especially because yes, the kind of vanilla version of first order local recurrency theory is that it's the strength of that first order local recurrency that gives rise to the subjective experience. But I think that if you allow them a little bit of leeway and you end up saying, well, maybe it's the trial by trial variability or the overall kind of stability of that first order recurrency that might lead to crossing of kind of a subjective experience threshold more often. So you have a very wide distribution under inattention versus a narrow distribution under attention. And you set a single threshold, then you end up with more signals that end up being more vivid or something like that. So there are first order explanations that might be compatible with subjective inflation. And I think that as we go into building some computational models to describe these behavioral data, we may end up kind of discovering that first order theory can not lose simply by modifying just a tiny bit, and that first order explanations might still be okay. So it was a weak challenge. It's not like a very strong challenge to first order approaches. And the neuroimaging will be kind of the critical nail in the coffin or not. Yeah. Yes.
And maybe to sort of play devil's advocate, whereby Victor Lama is the devil in this case. I mean, what you're asking them is to report their vividness. So the inflation is not necessarily about the experience; it's about the report.
Yeah, I mean, and this is a problem with anything that has to do with subjective experience in general. Is that like maybe it's just I told you that I was more confident, I had like a response bias, or I told you that it was more vivid. So to the extent that this is a problem for any studies of subjective experience, I think that's challenging for sure. I do think, though, and I went through this a little bit in the paper on introspective psychophysics that I've just put out. I think that if we say that it's a challenge that maybe you're just lying about your subjective experience or it's just about the report, that challenge kind of bleeds into a lot of other behavior that we do. So, maybe not in mice, but in humans, maybe you just told me that it was left tilted when you really thought that it was right or something like that. I think that there are ways to get around that with different kinds of paradigms also. So here we're just doing kind of a rating scale, no experience, some experience, like, a good, strong experience. In the past, I've tried to, especially all the way down near the detection and consciousness threshold, get at this with more of a 2-interval forced choice judgment, where you show, like, here's a thing, decide what the thing is and like get a subjective impression of it. And here's another thing that's actually not there at all. Here's a nothing, and do the same task. And then that sets a floor on the subjective experience so that you create a 2 IFC at the subjective level. So I think there are ways to get around that problem. It's still going to be there, so it maybe not fully get around, but I agree that it's important to think about that. And I'm glad that this room is thinking about that for sure. Yeah.
I guess beyond sort of just participants maybe lying, I think Victor Lama would say this is you're measuring access rather than phenomenal consciousness.
That's also very possible. So none of the conversations that we've really had here get at, I think, phenomenal consciousness. I mean, IIT purports to get at that phenomenal consciousness. That's its goal. But a lot of the other theories kind of say, yeah, access consciousness, I'm happy with that. Global workspace theory, yeah, access consciousness. It's not really a theory of phenomenology. And a lot of these other ones are like, okay, well, let's deal with that later. Let's first get this part right. I think you're right, though, that like, if we want to get into A consciousness versus P consciousness, like most of these theories are about A consciousness. Yeah. We've got a few minutes that we could do for panel discussion, maybe. Yeah? Questions for everybody? We got started a few minutes late, so yeah. I'll get rid of this. Yeah.
Thanks so much. So if anyone has any direct questions for the panel.
Hi, I guess this is for everybody. Do you think it's worth having a separate program on consciousness research, or do you think that consciousness research is actually just kind of collating a bunch of different cognitive functions together?
Everybody in this room is studying consciousness, they just might not know it. Or you're studying unconscious processing because you don't really care. But like, yeah, I think that it should be very integrated.
I mean, I think there's an important reason to have a focus on it, given how important societally people view the folk psychology of consciousness as forming, say, a basis for moral concern. But I do think, personally, the rapid rise of social AI is going to reshape what we think of as consciousness. We're going to reimagine the scientific construct of consciousness based on the rise of these systems. I think it relates to the discussion we were having in response to the question earlier about the concept of consciousness that we have scientifically, and whether that is more of a functional cluster or an intrinsic property. And I think the rise of social AI is going to push us towards thinking of it as more of a functional cluster, because essentially it's going to be very hard to then say, well, what extra is there beyond the functionality of the system?
I think Anil is putting it in a very convincing way. The hope is that it will fade away the difference. We do conscious science, and in the end, it might be like the idea of live, living thing. The question of being a living thing, what's the essence of life, was a question that was valid 100 years ago and has faded away. And so the hope is of that the same will eventually happen with consciousness science as such. But we are clearly not there yet, and there are many very important questions. End of life, to just name one. AI, another one.
I'm wondering, when we are looking for neural correlates of consciousness, then we need to somehow measure consciousness to correlate it with some neural data, right? And across the presentations today, I had the perception that the way you guys measure consciousness varies quite considerably. So many of the measures of consciousness rely on people's report of what they subjectively experience. And Megan, you emphasized very much that that has to be separated from objective performance. But then other studies, Lars especially, I think your measures of consciousness relied a lot on objective performance, and you even mentioned a mouse study. So in the mouse, we can only measure objective performance. We will not get subjective reports of their experience from them. So do all those measures of consciousness, do they have something in common that justifies calling them measures of consciousness?
I think this is a really important question. I think this is really, really, really critical, is that we, as a field, as a community, we need to be more clear, more aggressively clear about what we really mean when we say we're measuring consciousness. Are we just measuring reportability? In that sense, yeah, a photodiode is conscious because it can detect when a light is on or not. And there are some famous studies that have been covered in like Scientific American and stuff that say, oh, crows have consciousness because we can find this neuron in the brain that responds to whether the light was on or not. Yeah, I don't think that doesn't to me count as measuring consciousness. So for me, it's about measuring the subjective experience beyond kind of the immediate response properties of the system. But I think that there is still hope for doing some of these things in animals. So one example would be the subjective experience that we have of feeling sure in a decision versus not sure in a decision, because that can lead to objectively measurable behaviors that don't necessarily have a verbal report associated with them. In animals, it would be how long is the animal willing to wait to hang out to get a reward that's on an exponential delay schedule. Or another one that we're kind of pushing on is does having a stronger subjective experience, all else being equal, objective performance capacity, detection capacity, everything being equal, but does have a stronger subjective experience cause you to be more willing to interact with your environment, more willing to take that leap across a river when you are more sure or when you have a stronger sense that you know how far away the other side is. So we're designing some experiments now to say, are you more likely to initiate goal-directed interaction with the environment when you have a stronger subjective experience? And then we can start to say, well, maybe there are some behaviors that better correlate with those subjective experiences and others that don't, and we can start to then really operationalize what we're measuring.
Maybe just building on that, I think it's a really important question. And I think it also goes back to the conceptual issues we were talking about earlier, that you can't control for everything, because then you're left with no functionality, right? So you can't control for report and behavioral performance. And so at some point you need to make a choice about what are the relevant functions that you're interested in. And in humans, going all the way back to bars and the contrasted method, we've been kind of treating report as the gold standard. And I think one attractive position is to say, okay, report is the gold standard, but that potentially gives us access to a cluster of functions that we as humans focus psychologically understand as consciousness. So philosophers call this the natural kind method. You know, there's a bit like Lars's example of life. Life is not just one thing, it's a cluster of features we can point to that underpin this concept. And I think we're going to move in that direction with consciousness science, but it will loosen the force of these objections, because it will say we do need to start with, say, subjective experience, controlling for other things scientifically, but once we get into the investigation of those properties, then perhaps it opens up a functional cluster that all hangs together, a bit like a functional cluster that hangs together to explain life.
We didn't discuss this today, but I think, one of my favorite theories is dendritic integration theory, which will be something measured predominantly in mice, and other conceptuals are based on that, and you can only use measures that do an intracellular recordings in some sense, but they might be essential for understanding the difference between anesthesia and non-anesthesia. And important in this context are the whole stream of research that's coming out of Marcello Massimini and the IIT, or complexity measure approach of minimal conscious state and sleep states and different conscious states, in which their complexity measure is a very good track or trace of those depth, of the threshold of consciousness. None of that requires any response.
Cool. So this will be the last one, and then we'll wrap up there. Thanks so much.
Okay, thank you. Thank you. That was a very interesting few talks and discussion. I've seen a lot of consciousness science coming up everywhere. Also at OHBM, there was some big selling of consciousness science going on. So I have a bit of a maybe difficult question. So I can remember a few years ago where interoception became this big thing, where everybody was like suddenly realizing that the brain is in the body and they might be connected. And now consciousness is a big thing, which is definitely also important. But now again, it seems like the brain is again isolated from the body in some sense. And also we're being very reliable and very precise and not very naturalistic and not very inclusive in some ways in this space again. I feel like a lot of things are repeating, but maybe it's just what I kind of see, and I can't see behind the scenes. The third thing I also see happening again is that we're focusing on a very Eurocentric view of things again, so that we're kind of doing what the LLMs are doing, kind of, biasing ourselves in one direction. So I was just wondering, is that an accurate view of what we're doing here, or do I just not know enough about the behind-the-scenes work that's being done?
Shall I start? I think there's lots of interesting points there, and I think that the connection to the body and interoception, that is a clear part of what consciousness science should care about. I think in terms of these theories of reality monitoring and the kind of signals that might be relevant there, we're definitely thinking about the role of interoception there as being signaling multimodal precision, and that might be connected to insular function and how that might change how you attribute reality to exteroceptive stimuli. So I think there's a lot of work to be done in that direction. But I think your critique is well taken, that we don't want to get too narrowly focused and become too vision-centric. Vision has dominated consciousness science for good reason for many years, because it's a well-understood perceptual system. But you're absolutely right that human consciousness is broader than just vision.
Yeah, totally agree. I'm a multisensory scientist by training, actually. So I, pretend to be a vision scientist now, but I came up through like visual haptic integration. And so I think that the role of, and some of the theories that I put up in that big list also are really about embodiment and how like you need to have not just, it's not necessarily a physical body, but that there's a component of subjective experience or conscious experience that is predicated on and relies on the fact that I have a belief that I am not my environment, that I am separable from my environment, and that then flows into this interoception approach. So I think that you're absolutely right that there is this massive focus on like, let's be brains in vats with eyeballs on the front and like show them Gabor patches, and that's kind of what we're going to do. And we should take care not to be so like kind of shoegazy about that, right? Like, or navel gazy or whatever the term is. We need to get out of that. And I think that that Colin Allen's signatures testing approach is also a really interesting way of integrating what we are doing with what Steve was talking about too, and Lars, this kind of cluster of signatures of consciousness, or signatures, clusters of behaviors, of functionalities. And so the idea there is that it's not just this one thing, but it's the interrelation among how all of these capacities play with each other, how they move with each other when they are present, absent, when they correlate, when they dissociate. And those signatures then allow us to make statements about this system and their similarity in their conscious experience, maybe. And I think that if we don't do that, if we do fall prey to the criticisms that you are rightly levying, that we risk studying visual consciousness of Gabor patches and not much else. And we really should not be doing that.
Cool. Wonderful. Well, thanks ever so much, everyone, for coming. And please, let's say thank you to our three speakers. Thanks a lot.
Thank you to Paul for putting this together. Yeah.